In this class so far, we've learned about vectors. So vectors are objects with both a magnitude and a direction. We've seen that we can draw them graphically and that by just drawing little arrows, and that the length of the arrow represents the length, also known as the magnitude of the vector, and then the direction the arrow is pointing represents the direction of the vector. So this all feels pretty straightforward. We've also seen that we can do algebra with vectors, which is to say we can add them together, we could subtract them, and then we can even multiply them by scalars. And then finally, we learned about unit vectors. Now, unit vectors are these things that have unit length, which is length 1, and they have point in some direction. And so really these are useful for carrying information about the direction of a vector. And then you multiply them by a scalar to contain the information about the length of said vector. So we've seen furthermore that if we want to draw some Cartesian coordinate system, which is to say x, y, and z coordinate system, we can do that and we could put our vector on that coordinate system. And then we can represent our vector by the vector components, which are really telling us where on the grid of this coordinate system the head of the vector lies when we put the tail at the center of the coordinate system. Though again, I've mentioned that a vector is defined simply by its direction and by its magnitude, and where I draw this vector does not matter. So what we're going to see in this video is that there are multiple ways of describing the information about the vector. Now, of course, we can draw it as we've seen, but now we'll really want to quantify vectors. And so in this video, we're going to see ways we can quantify our description of vectors. So let me share my screen with you. Okay, so really there are three equivalent ways we can represent a vector in sort of a quantified way. I guess there are really four ways, the fourth being drawing the vector the way that we've been drawing it. So here I've drawn vector A, and you'll see I didn't even draw the tail right at the origin because, as I said, the location of the vector doesn't matter. So I can draw it anywhere on this grid that I want. So we've learned that we can describe the length and the direction of this vector using its vector components. Now, previously I drew it, as I said, with the tail at the origin. So those were simply the coordinates of the tip of the vector. Here I drew it somewhere else. And so what you should really think of these coordinates as representing are sort of the run and the rise. So where run being how far to the right it's going. So if you count these boxes here, that's 4. So we would call this a sub x, this 4 here. And then it goes up 5, right? This is 5 little units on this grid. And that I would call a sub y. Sorry, that's a little sloppy. So 5 equals a sub y because it's how much the vector changes in the y direction. And 4 is a sub x because it's how many units it travels in the x direction. So this is a first way we could quantify our information about a vector. And really, these numbers 4 and 5 describe everything we need to know about the vector. If I give you the vector components, you could draw it automatically, and that's really all the information you need. Next, we saw that we could sort of think of building up our vectors using unit vectors. And that's really using the fact that, so for instance, 4x hat is a vector moving to the right in the x direction 4 units. So this green arrow down here is the vector 4x hat. 5y hat is a vector moving up in the y direction 5 units. So this green vector is indeed 5y hat. And then we know how to add these vectors together by putting the head to the tail. And so 4x hat plus 5y hat is indeed this vector A here. So this is an alternative way we could write down our vector. And again, this gives us all the information we need. So this is a way of building up our vector using unit vectors. Then I also mentioned this is, again, simply a notational thing, which is that often people will say I hat instead of X hat and J hat instead of Y hat. So you just have to remember I hat, J hat, K hat are the exact same things as X hat, Y hat, and Z hat in this class. So the last way we could describe this information about a vector is often referred to as its polar representation. This would be its representation in terms of components, either 1 or 2, you're really giving the components of the vector, which again, the components are these numbers 4 and 5. The polar representation gives you the direction and magnitude. And by direction, I mean some angle measured relative to one of our axes. So here this green line is parallel to the x-axis. And so I could tell you the direction of A by giving this angle measured relative to this line, which is parallel to the x-axis. So it turns out for this particular vector, if I were to actually measure it, this would equal 51 degrees. And it's very important whenever you are giving the particular angle to describe the direction of the vector, you need to tell me or tell whomever that you are measuring it relative to what axis and in what direction. So here I would say this is measured counterclockwise, right? Counterclockwise goes this way, the opposite of the direction of a clock, right? This angle is measured counterclockwise from the positive x direction, right? Whereas this is the positive x direction. Right, and that would be the complete information about the direction. If I just told you 30 degrees or 51 degrees in this case, you wouldn't know if that's measured, this way, or maybe the vector is pointing this way and this is my 51 degrees. You wouldn't know what it means. So it's important to always say, so this should really say 51 degrees counterclockwise from positive x direction. All right, so that would give you the direction. And then I could simply give you the length. If I were to actually put a ruler to this vector A and measure the length, I would measure that it is 6.4 units, where a unit is the length of one of these boxes. And remember, our notation for the magnitude of a vector is using absolute value bars, or sometimes I might also just write this simply as A, right? So no vector sign up top, right? Just simply A, not boldface or anything. And that often is also used for the magnitude of a vector. And this also is telling you everything you need to know to draw our vector. So giving any of these 3 pieces of information fully describes the vector. So furthermore, what that tells us is there should be some way to relate these numbers to each other. If method 1, 2, and 3 are all giving all the information you need to describe this vector, then there should be some way to mathematically relate, this 4 and this 5 to this length 6.4 and 51 degrees. And that's where trigonometry starts to come in. So let's say I give you a vector and I tell you its components, which again, I'm often going to write the components. So again, this is AX and AY are the components, which again are just going to be some units or some numbers that might have units. In this case, it would be 3x hat plus 4y hat, and I could figure that out by counting these boxes, 3 and 4. Right, so let's say you're given the components of a vector and you want to figure out, well, what is this angle and what is the length of A equal to? How could we figure that out? Well, what you'll notice is if I draw this triangle on this Cartesian grid, I can draw over it, if I draw this vector on the grid, I can draw over it a triangle, right? It really forms a right triangle where this angle here is 90 degrees. And the length of this side of the triangle is the x component of our vector. And the length on this side of the triangle is the y component of our vector. And so all I need to do is to remember my trigonometry in order to determine this angle theta sub A, and then the length of the hypotenuse. The magnitude of our vector is always going to be the length of the hypotenuse. And so all we need to use, this is Pythagorean's theorem, which is a squared plus b squared equals c squared, using the standard variables that are used when you usually quote Pythagorean's theorem. And this is using the definition of tangent, the second one. So tangent of theta is always opposite over adjacent. Again, if you remember it using SOHCAHTOA, this is the TOA part, tangent is opposite over adjacent. So again, let's draw this triangle over here just to really bury this home. The length of this side is the magnitude of our vector. The length here is the x component. The length here is the y component. Here's our angle. And so tangent of theta is opposite, which, what is opposite this angle? A sub y. So a sub y. And then what is adjacent to this angle? A sub x. All right, and if we want to solve for the angle, we just take the inverse tangent of both sides. And that's how we got this formula down at the bottom, down right here. All right, and this formula up above it, again, we got using Pythagorean theorem. And all I did was take the square root of both sides. Right, I took the square root of both sides. Remember in Pythagorean theorem, this is a, oh, sorry, Siri thinks I'm trying to talk to her. This is A here, B. The A and the B's are the shorter sides. It doesn't matter which one you call A and B. The important thing is C is the length that's along the hypotenuse. So this formula simply comes from Pythagorean's theorem. So in summary, if you are given the components of a vector, which by that I mean AX and AY, then you can find the magnitude or length of a vector using this top formula, and then you can find the direction of the vector using this bottom formula. These formulas you will not need to memorize in this class. On exams, you will always be given formula sheets, and so memorization, in my mind, memorization is not what physics is about. It's about understanding how to apply these formulas. All right, so what if instead of giving you the components, I gave you the magnitude and direction of the vector? So I said I have some vector that is 5 units long, up pointing at 30 degrees, measured counterclockwise from the x direction. How could I find the components? Well, again, this is just trigonometry. So again, we see we have some triangle here, but now what we're going to need are our friends sine and cosine, right? So here, sine, right? Sine is always going to be opposite over hypotenuse, whereas cosine is always adjacent over hypotenuse. In this particular case with the triangle as I've drawn it, if we're interested in this angle theta shown here, the side opposite to theta is a sub y. And that's why I'm using sine theta with a sub y. And then cosine depends on the adjacent angle, which is a sub x. And then the hypotenuse is always going to be the length or magnitude. And so using both these formulas, I simply multiply both sides by the magnitude to solve for the components a sub y and a sub x. So these are the formulas that you will need when you are solving for the components. Now, one thing to keep in mind, the y component of a vector is not always going to be associated with sine, And the x is not always going to be associated with cosine. Sometimes these will be switched. When will they be switched? Well, it's because it depends on which angle you are given. If instead I gave you this angle, which, sorry, this is getting tight here, which maybe I call phi. So I give you the angle as measured clockwise from the y-axis. Then I would find that a sub y is a cosine of phi, and a sub x would be a sine of phi. All right, and that's because the right triangle I would draw if I was using phi would be this blue triangle instead. All right, so then that would cause me to, what I'm calling opposite and what I'm calling adjacent would be different for the angle phi. And so it's really important, whenever you do these, don't try again to memorize these formulas. What you need to remember is SOHCAHTOA, and then always go back to sine is opposite over hypotenuse and cosine is adjacent over hypotenuse, and then you'll always get the right answer. All right, so that in this sort of longer video, we discussed the different ways we could represent a vector in a way which is quantified, giving either its magnitude and its direction, or equivalently its components. And then we saw how, if you're given the components, how could you find the magnitude and direction? Or if instead you're given the magnitude and direction, how could you solve for the components?